Did you know that every single electron in the entire universe has a unique four-part address? It's like a secret code that tells us exactly where it lives and what it's doing. These are the quantum numbers, and honestly, understanding them is the key to unlocking the blueprint of matter itself. So let's decode it together.
You know, for the longest time, we all pictured electrons orbiting the nucleus like tiny planets. It was a really neat, orderly picture. The only problem? It was totally wrong. Modern physics came along and replaced it with this, the electron cloud. It's not a path, it's not an orbit. It's a map of probabilities, a fuzzy region of space where an electron is just likely to be at any given moment.
So that creates a pretty big problem, doesn't it? I mean, if it's all just a fuzzy cloud of probability, how do we describe one specific electron? How can we possibly tell it apart from another, especially in a big atom with dozens of them? We need a system. We need a unique address for every single one of them.
Okay, so here's our game plan. We're going to start by defining this whole address system. Then we'll break down the numbers themselves, cover the rules they absolutely have to follow, and finally, we'll use all of that to build an atom's actual blueprint.
So how in the world do you bring order to that chaotic cloud? Well, the solution is surprisingly elegant. Instead of simple x, y, z coordinates that we're used to, we use a specialized set of 4 quantum numbers to describe the precise state of any given electron.
And here they are in all their glory, the quantum numbers. Together, these 4 numbers create that complete 4-part address that you've been looking for. They describe an electron's energy, the shape of its orbital, its orientation in space, and even its own unique properties.
All right, let's start building this address. We're going to begin with the 2 most general pieces of information, the main energy level and the shape of the electron's home turf, its orbital.
First up, we've got the principal quantum number, which we just call n. This is the big picture. Think of n as the city the electron lives in. Is it really close to the downtown nucleus in City 1, or is it further out in the suburbs of City 2 or 3? A bigger n just means the electron is, on average, further away and has a lot more energy. So, if n is the city, what's next? Well, that's the subsidiary quantum number, L. Think of L as the type of neighborhood inside that city. It describes the shape of the orbital the electron is in. Now, its value is tied to n. It can be any whole number from 0 up to n-1, and we give these neighborhood shapes letter codes. 0 is an s orbital, 1 is a p, 2 is a d, and 3 is an f.
Now, this visual here really pulls it all together. You can see that the first energy level, n equals 1, only has an s sublevel. That's it. But look at n equals 2. It has both s and p sublevels. Level 3 has s, p, and d. And notice something else. Within any single energy level, the s orbitals are lowest in energy, then p, then d, and then f.
Okay, so we've got the city and the type of neighborhood. Now we need to get really specific. It's time to zoom in, find the exact house on the street, and even describe the resident living inside. This brings us to the third part of our address, the magnetic quantum number, or m sub L. This tells us the specific orientation of that orbital shape in 3D space. Its possible values are tied directly to L, ranging all the way from negative L up to positive L. This is basically the specific street that the house is on.
Let's break this down with the table here, because it makes it super clear. For an s sublevel, where L is 0, there's only one possible value for m sub L, 0. So there's just one s orbital. But check out the p sublevel. Since L is 1, m sub L can be -1, 0, or +1. And that's the key. This means there are 3 different p orbitals, each with its own orientation.
So what does this orientation actually look like in 3D space? Well, check this out. An s orbital is just a sphere, so it only has one possible orientation. But a p orbital has this cool dumbbell shape. That means it can be lined up along the x-axis, the y-axis, or the z-axis, giving us 3 distinct orbitals for those 3 m sub L values we just saw.
All right, we're on the last piece of the puzzle, the spin quantum number, or m sub s. Now this one's different. It isn't about the orbital or its location, it's about the electron itself. It describes a property of the electron that's kind of like its own internal rotation. And it can only have 2 values, that's it. Positive 1/2, which we call spin up, or negative 1/2, spin down. And this leads to a really crucial rule. Any single orbital, any one of those specific street addresses we've defined, can hold a maximum of 2 electrons, no more.
And if it does hold 2, they absolutely must have opposite spins. One has to be spin up, and the other has to be spin down. No exceptions.
So, we've got our 4-part address system. But atoms don't just fill these addresses randomly. Oh no. There are strict zoning laws that every single electron has to follow. Let's dig into the 3 big ones.
The most important rule of all is the Pauli exclusion principle. It's so simple, but so profound. No 2 electrons in the same atom can have the exact same address. All 4 quantum numbers can't match. This isn't a suggestion, it's a fundamental law of quantum mechanics. It's literally what keeps matter from collapsing in on itself and guarantees every electron gets its own unique space.
Next up, we have the Aufbau principle, which is just German for building up. And it's basically the universe's rule of efficiency. Electrons will always find the lowest energy orbital available to be as stable as possible. It's like water flowing downhill. They fill up the lowest energy spots first before ever moving to higher, less stable ones.
Now, here's where it can get a little tricky, because the energy levels start to overlap. But this diagram is your best friend. You just follow the diagonal arrows, and it gives you the exact filling order every time. 1s, then 2s, then 2p, then 3s, then 3p, and here's the weird part. You fill the 4s orbital before you go back and fill the 3d. This simple tool helps you get the Aufbau principle right every single time.
And that brings us to our 3rd big rule, Hund's rule. This one kicks in when you have orbitals of the exact same energy, like those 3p orbitals. And it's all about minimizing repulsion. Electrons are all negatively charged, right? They want to stay as far apart as possible. So think about it like getting on an empty bus. You take an empty row of seats for yourself before you sit right next to a stranger. Electrons do the same thing. They'll each take their own orbital in a sublevel before they ever start to pair up.
Let's look at a perfect example, nitrogen. It has 7 electrons. The first 2 fill up the 1s orbital. The next 2 fill up the 2s. That leaves 3 electrons for the 2p sublevel. Now watch Hund's rule in action. 1 electron goes into the first p orbital, 1 into the second, and 1 into the third, all with the same spin. They spread out first. They only pair up when they absolutely have to.
Okay, so we have the address system and we have the rules of the neighborhood. Now we can finally put it all together to write the blueprint for any atom on the entire periodic table.
And really, this is the ultimate takeaway here. The electron configuration that we can write using these numbers and rules, it isn't just some abstract code for chemists. It dictates everything about an element: its size, how reactive it is, the way it bonds with other atoms. It is the fundamental source of its entire chemical identity.
So there you have it. We've laid the foundation. We can now describe exactly where every electron lives and, more importantly, why it lives there. This blueprint is what allows us to understand the periodic table, predict how chemical reactions will happen, and even design brand new molecules. So the real question is, with this powerful knowledge, what are we going to build?